Hello, how are you? I hope you had a great weekend. So today we will continue with the last lecture on the basics of logic design. So with this we will finish all the, let's say, new content of this part of the module, the architecture part. And then in the last two lectures, tomorrow and the day after tomorrow, we will review some topics. I have just posted in the Q&A chat. I have just posted a form which will be available until tomorrow at 9 a.m. because I need to prepare the topics you would like to review. So you will have until tomorrow and at 9 a.m. to vote, and the topics more voted will be the ones we will review. Then also regarding the last lab, I know that there has been a lot of confusion with the exercise 2 in part 2 for the binary division. So what we have done is we have created, we have added another video updating that part. So basically the beginning of the video is just the same. What changes is the last part, and hopefully with that is clear. If it's still not clear, just let me know, please. So yeah, I think that's everything. So now we are ready to start. So remember that, as always, part of the material shown in this slide is taken from the book. So today we will see sequential logic blocks. So until now, we have only seen combinational logics, which are combinational logic blocks, which are the ones which do not contain memory. They just depend on the inputs. But here today we are discuss sequential logic blocks. In this case, these logic blocks depends on the inputs and also in a value stored in memory, which is usually referred to as a state. Okay, so the first of these sequential logic block we are going to see is called clock. They are used to know when to update an state. Remember that a state is a value contained in memory. So with clocks, we control when a state should be updated. It's just a signal which has something which runs periodically. So for instance, here we are drawing, we have here the clock signal, okay, which you see goes up and down. So in this case, the down will be when the signal is 0 and up will be when the signal is 1. Okay, so then usually what we do is during the clock period, we usually do data transfers and computations, and usually the states is updated at some point. Usually, well, in this case it's drawn here, but it usually happens when the clock changes, for instance. Okay, so here we will be doing in the blue parts data transfer and computations, and here we will be updating the state. Okay, so in clocks we have two things to take into account. The first one, and very important, is the clock period or cycle, which is the duration of a cycle. For instance, if I have the signal, remember it's 0, then it goes up to 1, and it goes down to 0 again, and then everything is repeated. So this will be the clock period. It means the part which is repeated. So everything is repeated, let's say, in 1 second. Or in this case, to have a more realistic measure, each clock cycle takes 250 picoseconds. I have here put a table with the conversion from 1 millisecond, microsecond, nanosecond, and picosecond. So usually the clock period is measured in picoseconds, but yes, you can assume that this period is the duration of a clock cycle in seconds. Okay, and the other measure, the other metric is called clock frequency or rate, which is just the cycles per second. For instance, imagine that I have 3 cycles. Then if those 3 cycles take 1 second, the clock frequency will be 3 cycles per second, in this case 3 Hertz. Okay? So this clock frequency is usually measured in Hertz, and probably you are familiar with gigahertz, which is, for instance, when I say that my computer, the processors of my computer are running at a speed of 4 gigahertz, I'm referring to this, to the clock frequency, okay, to the cycles per second in which my processor can do things, okay, can update state elements. I have here put also a conversion from kilohertz to, in order you to know how to convert from the different values to gigahertz, which is probably the most popular today. Time ago it was megahertz. And something very interesting here is that the frequency, the clock frequency, also referred to as the clock rate, is the inverse of the clock period. So we will have this formula. With this, I mean that is, for instance, remember that in the previous example, we have said that the clock cycle duration was 250 picoseconds. So then, if we have this value, the clock period or the clock cycle, the inverse will be the frequency. So we just divide this and convert from picoseconds to seconds, and then here from hertz to gigahertz. Okay. So now I have an exercise for you. It's very simple. So I will post a link to a form. I give you 1 minute. So I just would like that you calculate a clock frequency when I have a clock period of 400 picoseconds. Okay, the link is in the Q&A, so I give you 1 minute. I'm going to, so the question is also in the Q&A, so I will just, I think it will be more useful for you having this here. Okay. So imagine now that the clock period is 400 picoseconds. So what I want to know is the clock frequency. Okay, the time is over. So let's check how many answers do we have. Okay, so here most of you got the right answer, 2.5. So we are going to see how actually this answer is calculated. Okay, so we have mentioned that the frequency is the inverse of the period. So we just need to apply the formula. So 1 divided the clock period, and I have also shown you the conversion from picoseconds to seconds. So it's just 10 power minus 12. And if we do this calculation, we get the hertz with 10 power 12. And if we move the point to the right and 3 positions, then this 12 goes to this 9, and this is in gigahertz. Okay. Okay then. So now I would like that you do the inverse operation. So now I have an exercise in which I give you the clock rate and I want the clock cycle. So again, I will give you 1 minute and I will post a link to a form in the Q&A. Okay, so time is over. Let's check how many responses do we have. Okay, so we have 22 responses so far. Most of you got the right answer. And let's see how this answer is calculated then. So if the clock rate, remember that clock rate is a synonym of clock frequency and that clock cycle is a synonym of clock period, right? So if we know that the clock frequency is the inverse of the clock period, we know that the clock period is the inverse of the clock frequency. So then we just need to apply the formula. In this case, we have 2 gigahertz. We know that gigahertz is 10 power 9 hertz. And if we do the inverse, we got this value. And if we usually, you can leave it in seconds, but this clock cycle is usually referred to in picoseconds. So we will have the answer. Okay. Okay then. So in a clock cycle, we have seen we have the low value and we have the high value, and we call, when we go from down to up, we call this the rising edge of the clock cycle, and we go to up from up to down, we call this the falling edge of the clock cycle. And the clock period is the time of one full cycle, which is repeated and repeated. So in this case, this is one full cycle, which is repeated and repeated. So this will be clock period 1, this will be clock period 2, and then this clock period is divided in 2 portions. When the clock is high, as I was mentioning, so we have, in this case, what you see in blue is where the clock is high, and then when the clock is low, which is the one you see in red. Okay, so in this lecture we will use an edge triggered clocking. That means that an state changes when we are in a clock edge. So it could be the rising edge or the falling edge, but changes will happen when we are at those edge of the clock. Okay. So this is what we have mentioned. An edge trigger clocking will be then when state changes happen when we are on the clock rising edge. It could also happen when we are on the falling edge. It's just a decision of the programmer if we want the changes happen in the rising edge or in the falling edge. For instance, here we have the same example we have seen before, and now it makes more sense. So here we are updating the stage when at the rising edge. Okay. So this is what I have shown you before, but now we know that everything, this update in the state is happening when at the rising edge of the clock. And state, when we say a state memory, state or state element, we are actually referring to an element in the memory. Okay, just to be sure that we know what we are talking here. So well, we have also mentioned that during the clock cycles, what we do are data transfers and computations. This is what we do with the combinational logic we have seen in previous lectures. And these states here, for instance, here and here that are updated in this case, we have mentioned at the rising edge. So here the state is updated, then we apply some combinational logic to transform this to make computations, and then we update the state element again at the next rising edge. So with this, you see that, remember that the combinational logic blocks only had inputs and outputs, but now with these elements, we are capable of storing the inputs and the outputs of those combinational logics blocks. Okay. So this is what I have already mentioned, and now it's in the slides for you when you study. Okay then. So an interesting thing is that in this methodology we can read and write elements of the state elements in the same clock. So in the previous slide we have the state element 1, combinational logic, and state element 2, but actually we can do this in the same clock. That means that I can have this state element, then this state element can be the input of the logic of the combinational logic, and also can be the output. Okay, so this read for having the input and write again for the output can be done in the same clock. Okay, so at this point here, this state element can be used for the input of the combinational logic of the next cycle, and as output for storing the output of the combinational logic of the previous cycle. Okay, so what we are doing here is that this state element 1 combinational logic state element 2 actually is converted to a loop in which we only have one state element, because this having this read and write at the same time can be done in the same clock. Okay, so now that we know what is a clock, let's see in more detail how elements are stored in memory. So the more basic elements are called flip-flop and latch, and those elements are very similar. The only difference is that with the flip-flop we only update the memory element, the state, only at a clock in a clock edge. In this case, remember, we have been using the rising edge, but it could also be the falling edge. And the difference with a latch is that in the latch, the state can be changed at any time. Whenever the clock is asserted, which means whenever the clock goes up, the input can change. It doesn't matter if that change in the clock is in the edge of a clock cycle. It can be anywhere. Okay, so the difference is that a flip-flop only changes on a clock edge, and the latch changes whenever the clock changes from 0 to 1. And in computers we use those two simple elements, the flip-flop and latch, for storing a signal. So right now with this, you know how actually those zeros and ones are stored in memory. So for instance, let's take a look to a D latch. So it has two inputs. One is the data to be stored, and the other is the clock signal. and then the outputs will be the value of the state or the value of the memory element, and it also gives us the inverted of this state, the complement. So graphically, we will have this. And remember, we have already seen what is an AND gate, what is an OR gate. We have seen that these bubbles here, the white bubbles, are inverters. We have seen that the black points are connections. So we understand what is happening here inside. This is just mixing AND gates, OR gates, and inverters in order to make this happen. So what happens here is when C changes from 0 to 1, this data here, this data input, will be in this queue. Otherwise, the value of this queue will be the value of the previous queue. Okay, so this is what we have here. If C is asserted, if C is 1, the latch, if C changes from 0 to 1, the latch is open. Is what we say. We say that the latch is open, and this means that Q will be equal to D. In any other case, what happens is that the latch is closed and Q will be equal to the previous Q, so it doesn't change. Okay. Okay, so graphically, so imagine here we have data and we have a latch, and we have said that the latch changes when the clock is asserted. So initially we see that here the clock is not asserted. Okay, so initially we have the clock is 0, and when this clock goes up to 1, it is asserted. What happens then? Then happens that Q will be equal to the value of D. So in this case, Q was 0 and D is 1, so Q will be equal D, which means that Q will be equal 1. And then this value is not going to change. The value of Q is not going to change until this C is asserted again, which means until this C changes from 0 to 1, which actually happens here, okay, at this point. So at this point, again, the value of Q will be updated. And in this case, D is 0 at this point, so Q is updated with that state. So this is a D latch, which is used for storing elements. So now for a flip-flop, we are actually using two D latch. So in this case, we are showing a flip-flop with a falling edge trigger, which means that it changes when the clock is at its falling edge. Okay, so we have that if C, the clock signal here, is asserted, then this latch here, which we call the master latch, is open and follows the input D. If C is de-asserted, which means that C goes from 1 to 0, then this master latch here is closed and the slave latch here or latch 2 is open and gets the input from the master latch. Okay, so we have latch 1 or the master 1 and the latch 2 and the slave or the slave latch, and depending of if C is asserted or not, when C is asserted, this latch is working and this latch is not working, and vice versa. And with this we have something similar to the previous D latch. Let's see this graphically. So here we have initially the clock, and we have mentioned that we are only to change at the falling edge here. Okay, so this D flop will only change at the falling edge. So here, when the C changes from 1 to 0 is the falling edge of this clock, then we will update the state, which will be Q equal to the value of D. And then this clock cycle will repeat again, and until we are in the next falling edge of the clock cycle, the state of Q will not be updated. Okay, so the only difference with the D flop and the D latch is that the D flop change periodically at the clock edge, and the D latch can change at any place in which the clock changes its value. Okay. So now, with this information, we are ready to see how actually registers, remember the registers we were using as operands in the arithmetic operations? So with this information, we can see how register files are created. So for creating a register, we just need a decoder and a D flip-flop, well, several D flip-flops. And so we indicate the number of register to the decoder, and if we want to read or to write it, and using a decoder and the D flop, we can update this value or only read that value. Okay, so I don't expect from you that you completely understand how to create a register file. What I expect is that at least you know the basics and have an initial idea of how a register file is created. So we have seen what a decoder is, we have seen what a D flip-flop is, and now you can more or less imagine that using a decoder and those D flip-flops, we can have different flip-flop for each register, and then we will be able to update those registers with the flip-flops. Okay. And finally, another memory element that probably you are very familiar is called the SRAM or DRAM memories. I think you are all familiar with these terms. So remember that one of the components of the computer we mentioned in the first lecture was memory. So in this case, we have actually the memory, the main memory, and also we have registers that is like an internal memory for the arithmetic logic unit. So the registers we have seen how are created with decoders and flip-flops. Okay, but for a larger amount of memory, which will be the memory, the main memory, the memory connected to the process, outside the processor, we use what it's called static random access memory or dynamic random access memory. I'm just mentioning those names for completeness. I don't expect from you knowing how those types of memory work. This is just for completeness and for you having an initial idea of how these elements are created. So the static memory, the static random access memory, or the static one, data, as its name indicates, the data is stored statically, whereas with dynamic random access memory, this data is stored dynamically. In general, we say that RAM memory is faster than the RAM, and the problem is that RAM is less dense, which means that in the same space I can have less memory in a SRAM than in a DRAM, and for that reason the SRAM is more expensive than the DRAM. And as you can imagine, if the SRAM is faster, we use it for registers because registers need to be read more frequently, and DRAM is used for main memory, which is not read as frequently as the registers. So coming back to our initial figure, so we have here the memory will be DRAM and the registers will be SRAM. Okay, so graphically, and don't panic. So this is just for completeness. This is just for you to show how it looks in logic circuit, how it looks an SRAM. So we will have an input here with the address of the SRAM I want to modify. In this case, I have 21 address lines, which give me 2 megas. Then we will have 16 data inputs and 16 data outputs, and with these three control lines, we select what we want to do. So we can write, or we can write a register, or we can read a register using those three control lines. Okay, as commented, this is just for completeness. I don't expect from you that you completely understand all what is happening here. It's just to make you start being familiar with these diagrams for the future. Okay. Let me check if we have any question. So someone is asking, what does asserted mean? So asserted means that the clock changed from 0 to 1. That means that the clock, a signal is asserted. Okay. So for instance, if we go here, so here the clock signal is 0. When it changes to 1, it means that the clock signal is asserted. And on the contrary, when it is 1 and it changes to 0, the clock signal is de-asserted. Okay? Let me check. Someone is asking on page 13, how do we get the 9? I guess you're referring to this 9 here. So we have seen, so someone is asking, how do we get this 9 here? So I have shown you previously here in this table that 1 kilohertz is equal to 10 power 3, and we have also seen that 10 power 9 is equal to 1 gigahertz. Okay, so if we go then back to the page 13, we see that 1 gigahertz is converted to 10 power 9. I think you were referring to that. Okay, someone is asking if I can explain again the flip-flop. So yes, we will repeat the flip-flop. So here what we have is two D latches. So the flip-flop is actually composed of two D latches, and this is called the master latch, and this is called the slave latch. So when this latch, the master one, is open, the slave one is closed. So we have the input here, and then this latch will be activated when C is asserted, when the clock changes from 0 to 1. And the input D will go here, and the state of Q will be updated accordingly. But as this latch will be closed, nothing will change here. Okay, so when C is asserted, the master latch is activated and the Q is modified. Then when C is de-asserted, which means C goes from 1 to 0, this latch stops working, so the input D is not used. And what happens here is that we are using the output Q from the previous master latch, and in this case, the slave latch is working and the Q state will be updated. Okay, so those are like complementary latches. One, when this is working, the slave latch is not working, and vice versa. Okay, so the purpose of, someone is asking what is the purpose of the flip-flop. So the purpose of the flip-flop and of the D-latch is storing elements. I am showing you here how do we actually keep an element in a register or in memory. So this is internally what is happening. When I want to keep a bit 1 or a bit 0 in a register, internally what we have is something like this, and with this we are capable of keeping the state of an element and updating it when a clock signal happens. So in order to know, someone asked, when do you know if a latch is open or closed? So in the case of the D latch, we have mentioned, if you follow the outputs in here, so we have seen already this, and if you do the truth table for this, you will get when the latch is open. When the latch is open, it means that the state of Q is updated. Okay, this is what we are saying in this slide. When we say the latch is open, in this case, when C is asserted, when the C clock is changes from 0 to 1, we say the latch is open, and we say that the Q, the state, is changed, is updated. Otherwise, it is closed. Okay, so let's continue, and I will answer more questions in the end. So the last part, so we have seen today clocks, which is actually just a signal which periodically changes from 0 to 1. Okay, and then we have seen memory elements, which allows us, using a clock signal, update elements in memory. And now we are going to see something called state machines. You have already seen state machines in the context of networks, and here we are going to see state machines in the context of computer architecture, but the main concept is very similar. Okay, so we have seen that in sequential systems the outputs depends on the inputs and of something that we call a state, which is the content of the memory. And this cannot be described with a truth table as we have done with combinational logic blocks. So in this case, what we use to define sequential logic blocks is what we call state machines or finite state machines. Okay. So a state machine, it's composed of a set of inputs and outputs. This is the same as for sequential, as for combinational logic, but what changes here is that we have a couple of functions. One function will tell us which is the next stage, and the other function will tell us which is the output, will define what is the output. And both of them, the next state and the output, will depend on the inputs and outputs, okay, and also on the current state of the machine. The functions, those functions, the next state function and the output function, are implemented using combinational logic. So let's see graphically how do we represent this. So imagine that this is here we are representing a sequential logic block using state machines. So in this case, we have the state, which is here the current state. This is just the memory element, the latch, a D flip-flop, or whatever we are using here. And we need the clock signal in order to update this state whenever necessary. We have here the input, so this input will go to both the next state function and the output function. So with the output function, we will use the input, we will use also the current state, and using the input and the current state, we will get an output. In here, what we have is a combinational logic. Okay, and for calculating the next state, we do something similar. We use the input, we use the current state, and with some combinational logic here, we get the next state, which will be updated in the state in the memory when the clock signal has the appropriate value. Okay. So we can also represent this state machine in hardware, and in this case, we have this state machine, which is that what we have mentioned, the D latch or the D flip-flop or something similar for keeping storing the memory, the element, the memory element, and we have the combinational logic to perform the next state function and the output, calculate the output. And this is the hardware representation of a state machine. Okay. So this is what I wanted to show you today, how actually internally, using all the information we have seen in these lectures regarding logic design, we can build internally what is inside the computer. So I'm going to see some questions. I see some questions, some people saying that in this part of the module of the logic design, you are a bit lost. So it's completely understandable. So you are at level 1, and I know that those are very complex concepts. So I don't expect from you knowing all this by heart and knowing how all these complex concepts work. I expect from you knowing the basics and understanding the overall situation, and more or less understanding for what we need a clock, for what we need a memory element, and what is represented in a state machine. So these kind of things, the overall idea. So I'm not interested in the details, because I know that this is just level 1. This is just a starting point to getting used to this to this representation of hardware using this kind of logic blocks. So now I will try to address more questions. Someone is asking if the exam is open book. Yes, it's open book. Someone is asking when will we get the practice paper. So the exam paper is now being reviewed by the moderator. So what I expect is that this week we will finish the lectures and the last lab, and next week we don't have lectures and there is no exam. The exam is in 2 weeks. So hopefully by the end of this week I will have the approval from the moderator, or by next week. So you will have time to see the practice paper, and we will have time also I will also upload the solution. So we will be doing something similar like with the lab. So I will publish the practice paper. I will give you a couple of days to give you enough time to try to solve it, and then I will publish the questions. Okay. Let me see if I see any. So people is getting confused on when the D latch is asserted or deasserted. So when the signal change. So you can, if you see this logic here, you can you know how to create the truth table for this. So the truth table will have 2 inputs. One will be C and one will be D, and 2 outputs. Well, in this case, it will be only 1 output, because the second output is the first output inverted. So you can do combinations. So in this case, we are saying that if this C is 1, okay, C is asserted, C is 1, then the latch is open. which means that this data here, this D here, will go to this Q here. So if C is 1, this Q will be equal to the input D. Okay? If C is 0, the latch, we say, is closed, and then Q will not be updated. Q will have the same value as before. Okay? So this also answers another question which was asking when is the latch open, when clock is 1 or 0. So when C is 1, the latch is open. When C is 0, the latch is closed. Okay, let me check. So the assessment, how long is the assessment? All this information is already in Canvas. It's 2 hours. I assume that all of you regularly check the Canvas page and all these kind of things. But yeah, so the exam is 2 hours. You have in the Canvas calendar, you have the date and the time for the exam. Okay, you go to the calendar. I'm checking it, but I'm pretty sure that it's there. Yeah, there it is. The exam on the Canvas page is on the calendar. So you have here from 2 p.m. to 4 p.m. we have the exam. Okay. So regarding the type of the exam, someone is asking if we will get essay questions. So you will get a practice exam. I'm not capable of answering this right now because the moderator needs to approve them, but you will see a practice exam which will be similar to the one you get in the final. So do not worry about the type of question. Someone is asking also regarding the exam. Will be if I will be asking something that has not appeared in the lectures or in the textbook. So the exam is open book. So I will for sure not answer something that I have already done in class. What things that I can do? For instance, consider the last lab you have done, lab 3. You have learned how to divide and multiply. Maybe I could ask you to do a multiplication or a division using the enhanced hardware, but changing the inputs. Okay, maybe for sure I can give you different inputs and maybe also varying the number of bits of those inputs. That would be something that I could do. Okay, so it will be things that you have seen in class, but obviously there will be something different. Otherwise, you will just need to copy and paste. Okay, someone is still. Someone asked if with the labs will help you to answer the exam. Yes, so in labs what we see is the material we see in lectures, and sometimes we even advance that material. So for sure the labs will be very helpful for the exam. Okay, and someone for finishing, someone would like that I go again for the example of clock frequency and hertz. So I think you refer to this exercise. So here I have asked you if the clock rate is 2 gigahertz, which is the clock cycle. So we have seen that the clock frequency is the inverse of the period, which is the same as saying that the clock period is the inverse of the clock frequency. Then if we apply this formula, we just have that the clock period is the inverse of the frequency. So here, if the frequency is 2 gigahertz, we have that 1 divided 2 gigahertz will be the clock period. So gigahertz, we have seen that is the same as 10 power 9 hertz. So if we do this division, we get 0.5 multiplied by 10 power minus 9 seconds. And as I have mentioned you, this is the clock period is usually referred to in picoseconds. So for converting to picoseconds, we just move this point three positions to the right in order to increase this exponent to 12, and we know that 10 power minus 12 is equal to pico. Okay, so we have two lectures for reviewing tomorrow. So I will be asking all your questions, so you don't worry. And if we need extra sessions for answering more questions, don't worry, we have time. And don't be worried about the exam. I know that this last block of logic design is a bit complex. So in the exam, don't worry, I will not be asking very difficult things. So my intention here is that you get familiar with logic design and with this with this way of representing hardware and so on. But I understand that this is level 1, and this material has a complexity. So this is just a starting point. So you will not be asked very complex things. So yeah, I hope you have enjoyed the lecture. See you tomorrow. Remember that there is a form for voting what you want we review tomorrow and the day of after tomorrow. Have a nice evening and rest of the day, and thanks for listening. See you tomorrow. Bye bye.